Okay, binary search trees. Yeah. So binary search trees. Hopefully we all know what a search tree is by now. But values in the left subtree are smaller than the values in the root. Values on the right are bigger than the root, and the left and right subtrees are also valid binary search trees. And if we flatten the binary search tree, or we do an in-order traversal, it's in order. To insert into a binary search tree, we just keep going down until we find somewhere we can put our node, and then we just insert it there. And that's log n. Insertion is log n. Searching binary trees is log n, by just going down. But log n is the best case complexity if the tree is balanced. If the tree is not balanced, then it could be O of n, because we could end up just treating the tree as a linear, as a linked list. Yeah, and the average height of a general binary tree is O of root n. I'm not sure what general binary tree is referring to here, but I'd probably go with log n as your understanding of the height of a binary tree. When we want to delete from a binary tree, we can either insert all the items except for the one to delete into a new binary search tree, or we can do n inserts, each of which has this complexity, so that's O of n log n. Or we can, worse than deleting, yeah, and this is worse than us just deleting from an array, which we can do in linear time. Or we can find a node containing the element to be deleted. If it's a leaf, we remove it. If one of the node's children is not empty, replace the node with the root of the non-empty subtree. Else, find the leftmost node in the right subtree, replace the value to be deleted with that, and replace the leftmost node with its right child, which is O of log n. So, if we have something like this, and we wanted to remove this node here, then all we'd do is we'd say, okay, we want to get rid of this, so we take this node out, replace it with the leftmost child of the, or the rightmost child of the left subtree. We can do that, and we have our tree with the node removed. If we wanted to have a slightly bigger tree, something like this, I don't know. Okay, let's say we had this, and we wanted to remove this node here. We'd remove the node, and then replace it with the leftmost node of the right subtree, or the rightmost node of the left subtree. It's up to us how we implement that, but let's say we want the leftmost node of the right subtree, or the rightmost node of the left subtree, sorry. We'd take this node up, bring it here, and get rid of this. If that node had some children, for example here, then we'd still take this rightmost node up, and then we'd just make this have this node as the parent, and then get rid of that. So that's how you can remove nodes from a binary search tree, and that's log n. That's an example. I'll let you look through that if you want to. And this is how we can implement deleting from a binary search tree. We just make a new tree with that node being deleted, and we pass the result of that into our make tree method. Deleting from a binary search tree, smallest node. This just tells us the leftmost node of the right subtree. Yeah, so we can use this to get the smallest node, and we call that down here. Recursion, love it. To check whether a binary tree is a binary search tree, if the tree is empty, it's a valid binary search tree. If the tree is not empty, then it's only a valid binary search tree if all the values on the left are less than the root, all the values on the right are greater than the root, and the left and right branches are also valid binary search trees. And this is how you can recursively check for that. This is quite a nice recursive method. All smaller and all bigger, just check every node and make sure that they're all smaller and all bigger recursively. Okay. Sorting using binary search trees. We can do an in-order traversal. So you can imagine this as, how I learned it at A-level at least, is imagine we have a dot under every node, like this. An in-order traversal is going to look at left, and then node, and then right. So you can imagine it as looking at this node, then this node, then this node, this node, this node, this node, this node, this node, this one, and then this one. Okay, so we look at all of the nodes in that order. So if this was a sorted binary tree, say we had 1, 2, 3, 4, 5, 6, 7, 8. Sorry, 7, 8, 9, 10. This binary tree is sorted. Everything on the right is greater and everything on the left is less. So this is a valid binary tree. And if we do an in-order traversal, we'll end up with the values out in this order. So we can get them in order using the same sorting convention we used when we inserted into the binary tree in the first place. Cool. So we can just insert everything into a binary tree and then print it in order to sort of carry out that binary search. And that's O of n log n. AVL trees. Okay, so an AVL tree is just a balanced binary search tree. The height of a node is the length of the longest path from that node to a leaf node, and the balance at a node is the height of the left subtree minus the height at the right subtree. So if we had this tree here, what would be the height of this node here? So the height is the length of the longest path from that node to a leaf node. The longest path from here to a leaf node is 1, 2. So yeah, nice job. This would have a height of 2. What would be the balance at this node? -1. Yeah, good. So the height at the left subtree is going to be -1 minus -1, so 0. And the height at the right subtree is going to be 0 minus -1, so 1. And so the balance at this node is going to be height at the left minus height at the right, which is going to be 0 minus 1, which is just -1. Okay, so the idea of an AVL tree is the balance at every node is 0, 1, or -1. And so that doesn't check out for this node, for example, because the balance at this node is going to be 0, minus 1, 2, 3, 4. So balance here is going to be -3, sorry. So the balance here is going to be -3. That is not in 0, 1, -1. So this is not an AVL tree, because not all the nodes have a balance in this set. So what we have to do is we have to balance this tree. You wouldn't really balance a tree like this. You'd balance it after an insertion if the insertion causes the tree to be unbalanced. So there's 4 cases you need to be aware of. So we have left, right, right, left, 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 right, right. And this refers to the rotations we do. So yeah, we wouldn't actually end up in this position in an AVL tree, just because as we insert at every stage, we always make sure it's balanced. But yeah, say we had something like this. So our left, right, right, left, right, right, and left, left. Okay. So a left-right rotation is when our imbalance is sort of a left-right imbalance. So let's say we had a tree like this, and we insert a node here. Right now everything's balanced. As soon as we insert a node here, it's imbalanced, because the balance at here is going to be 1, 2, minus 0, so 2. And 2 is not a valid balance. It has to be 1, 0, minus 1. So in this case, we've got a left-right imbalance. So first, we'd rotate this left. So we'd bring this down, bring this up, and rewire this, and that would be fine. Now we've balanced that. But we've not quite fully balanced it yet. And then we'd do a right rotation. So we've done a left rotation, now we do a right rotation. And to do that, we'd bring this one down, bring this one up, and bring this one up. And that would be our sort of balancing method for that. If we had a right-left, it's the same, but it's the opposite. So say we had something like this, and we had, I'm going to do it in a different color. We insert here, and then we insert here. So when we insert this first one, this is fine, because everything's still balanced. As soon as we insert the second one, this one's out of balance all of a sudden now. This one's going to have a balance of -2. And so we need to rebalance that. So first we do a right rotation. So we move this down, we move this up, and we connect that up. Okay, it's still not balanced, so now we have to do a left rotation. So we move this down, move this up, move this up, and now our tree is balanced. So it's exactly what we've done in the, but just like the other one, but flipped. So let X be the lowest node where an imbalance occurs, following an insert into subtree Z. So if we insert something into this Z, X is the lowest node where an imbalance occurs. So in our case, our lowest node which had the imbalance was just this root node, because all the other nodes were balanced, even though it was 1 or -1, they're still balanced. This is the lowest node where there's an imbalance. So we look at that, and then we rotate the things beneath that. So, for example, with the right-left, it would look something like this, where this is the imbalanced node, and this is where we inserted. And so that's how we decide which ones we're going to be rotating. So let's just go over that RL one again, but use that sort of systematic way of deciding. So we had something like this. If we insert this node here, the lowest node where we have an imbalance is here, actually. So the imbalance here would be -2. So this is the node we're going to be, this is going to be our X, this is going to be our Y, this is going to be our Z in this RL in this RL diagram. And then as per the steps we take for that, we then, first we do a right rotation. So first we move this Y down here, we move this Z up. And then the lowest node where an imbalance occurs is still this one, but now it basically becomes a right-right rotation. So we just need to rotate it left. We take this one, or we take this one down, we take this one up, and we take this one up. And then we've balanced that. Oh, right, yeah, no. So we kind of use the node that's, the first node that's imbalanced from the leaf nodes upwards, or the lowest node down that has an imbalance. So with the left-left, for example, say we had a tree like this, and we had this. Okay, so this is perfectly balanced right now. Yeah, Abdul Barry is, he's got a goated video on this. If we insert here, this is still balanced. If we insert another one, this isn't balanced anymore. What's the lowest node where there's an imbalance? So the lowest node here with an imbalance is this one here, because this has an imbalance of 2. This is just 1, so that's fine. This is 0, so that's fine. So the lowest node with an imbalance is this node here. Yeah, cool. So this is a left-left, because we've got a left node and then we've got another left. So this would be X, this would be Y, and this would be Z in this diagram here, LL. Okay, so here we move X down, Y becomes the new parent, and we move Z up. And in this case, we only have to do 1 rotation. We don't have to do 2 like the LR or RL ones. And so at this point, it's balanced. And similar with the right-right. So if we have something like this, and then we have this, and then we have this, the lowest node with an imbalance is this one, with an imbalance of -2. So if we label these again X, Y, Z, we want to move X down, Y becomes the parent, and Z is here. And so that's how we'd balance that tree there. Do those rotations make sense to everyone? How we're deciding which ones we're sort of, yeah, like closest to the root or furthest. The one that's the lowest down, so furthest, yeah. We look at the first imbalanced one that's furthest, and that becomes our X in this diagram, essentially. And if rotating causes any imbalances further up, we can sort of do it recursively, and then recursively shuffle up until the whole thing's balanced. So here we did a left rotation all the way up to, we rotated this 5 up, so then it becomes an LL instead of an LR, and then we did a right rotation there, so we can chain these rotations together. Yeah. To delete from an AVL tree, the general approach is to modify the delete algorithm by deleting the node from the tree using the BST algorithm, and as we return up the tree, we rebalance as necessary, just like we would for insertions. Cool. And then in terms of AVL trees, one other thing to be aware of is minimal AVL trees. Okay, so a minimal AVL tree is also just called a Fibonacci tree, and this is just a minimal AVL tree of some given height h. So if we have a height of 0, our minimal AVL tree is just a single node, because we can't have no node there, because then it wouldn't be a height 0. If the height's 1, then we can either have this tree here, or we can have this tree here, where the size is 2. If the height is 2, then we can have any of these 4 trees. And if the height is 3, we can have 8 other combinations of trees, and so on and so on. But what we want to sort of be aware of is the size of these trees. So if we have a minimal AVL tree, let me fix that here. Okay, so if we have a height 0, height 1, height 2. Okay, so a height 0 minimal AVL tree is just going to be a single node. So this is just going to be 1. Height 1 AVL tree is going to be 2 nodes. So this is 2. And to work out the sizes of the subsequent Fibonacci trees, all we have to do is take the last 2 values, add them up, and add 1. So 2 plus 1 is 3. 3 add 1 is 4. And then for a height 3 tree, 4 plus 2 is 6, add 1 is 7. Height 4 tree is 4 plus 7 plus 1, so 12, 20, 33, 17, 12, okay, yeah. And that's how we can sort of work out this chain, and that'll be 54, and so on and so on. And that's how we can work out the sizes of these minimal AVL trees for a given height. And it's derived from the Fibonacci sequence. It isn't the exact same as this Fibonacci sequence, but that's just this formula here. And in general, we obtain the Fibonacci tree of height h plus 2 by taking the h and the h plus 1 trees and giving them a root node, basically. That's the graphical way of that Fibonacci sequence being represented. In terms of the methods we can use on a AVL tree, it's pretty much the same as a binary search tree, but it's always the best case. It's never going to be O of n, because we're not going to have a linked list. So search is O of log n, insert is going to be O of log n, and delete is also going to be O of log n, because it basically does what insert does. Cool, that's everything on AVL trees.